Okay, so in the previous video, we defined the covariance in this way, the sample covariance formula in this way. As I said, it is very similar to the variance formula. But it's actually a little more extended because there are two variables. But basically, the steps are pretty similar. We have to calculate the average of x and average of y first, and then calculate their deviation, like deviation of x, deviation of y, and then multiply them. Instead of taking square, we multiply those two deviations and then take the average. So the steps are pretty similar to the variance formula. We are going to practice that with a simplified data set. So, like the original data set was real, the graph was based on the real data, and it had 183 countries. And I'm going to show you how to calculate those real, like a large number of data on Excel. But for now, for practice, I will simply take 3 countries from the data and just assume that we only have 3 observations, and we would like to calculate the covariance only based only on these 3 countries, as if it's all the observations we have. Okay, so the 3 countries we are interested in are Canada, the United States, and Mexico. And we observe their temperatures and their GDP per capita. And I also simplified those numbers. So simply, I'll assume that Canada's average temperature is -5 degrees Celsius, and USA is 10 degrees Celsius, Mexico 25 degrees Celsius. And GDPs are also simplified. So the per capita GDP is 35,000 in Canada, 40 in USA, and 15,000 in Mexico. Right? So suppose that these 3 by 2 numbers are the data, all the data we have. So we'd like to see, is there any pattern between the two variables? So, like in this order, the temperature increases. As you go south, of course, the average temperature increases. And then, like, we hope if y was strictly increasing or strictly decreasing, then it would be very easy to determine the direction. If the GDP per capita increased in the same order, then their relationship must be positive. If they are strictly decreasing, then it must be strictly negative. But here, it increased from Canada to USA, but then decreased a lot from USA to Mexico. So when temperature increases, GDP first increased and then decreased, right? So we need to quantify the relationship to see the direction, the average direction. Here we have to say yes or no, like a positive or negative. Okay? How do we do that? It's simple. First, we have to calculate the average temperature, which is 10 if you do the algebra. And the average GDP per capita is 30,000 if you calculate, right? So suppose they are calculated. I'm not going to show you how to do that. Must be simple enough. And then the next step is subtract those averages from those observations. So the observations of x is -5, 10, 25. So subtract 10 from them. Then the deviations become -15, 0, and 15. So you can, as I said in chapter 4, you can understand it as a transformation of the original variable x. Now, subtract the average GDP per capita from the observations of GDP per capita, right? So 35,000, Canada's GDP per capita is $5,000 above the average. And the US, 40,000. And if you subtract the mean, it becomes plus 10,000. But Mexico, GDP per capita is 15,000, and then it is 15,000 below, so negative $15,000 from the mean. So deviation in the GDP per capita is calculated like this. So it's another transformation from y. Y is transformed into its own deviation. So we did like this transformation, deviation transformation in chapter 4. We are just doing the same thing for a pair of variables. And then multiply them. Simple. So minus 15 times 5,000 becomes minus 75,000. 0 times anything becomes 0. 15 times minus 15,000 becomes minus 225,000. Right? Then in the end, the summation is minus 300,000, and you divide it by the sample size minus 1. So the denominator is n minus 1 because we use the sample covariance formula now. So the covariance becomes minus 150,000. So this is the covariance. So what you can tell from here is, in the end, the covariance is negative. So the direction of the relationship is negative. On the graph, you can see the trend. So Canada, US, Mexico, and then you can draw a trend going down. So if you explain the 3 dots with only one straight line, it must be downward sloping. That's the best fitting line, right? So it's also negative. The negative slope is implied by the covariance. Okay, or like I did not have the graph, but if you make 4 quadrants on this graph, then US is exactly at the average of temperature average of X. So it's not included in either quadrant at all. But the Canada is on the 4th quadrant and Mexico is on the 2nd quadrant. So in both quadrants, they imply negative relationship. So in that sense, the overall relationship within these 3 countries is negative, right? So now I'm going to give you a chance to do your own exercise. Now what I'm going to do is I will transform the data first from Celsius to Fahrenheit, right? Celsius to Fahrenheit, if you do the transformation, it becomes 23, 50, and 77 Fahrenheit. Average temperature become like this. And then I will change the GDP per capita by deleting 3 zeros. I will measure the GDP per capita in $1,000, right? So earlier they had 35,000, 40,000, 15,000. So, but let's drop 3 zeros. So we have these numbers. So now we have new and easier numbers than before. Then now you can calculate the covariance between these newly defined variables W and Z. Try it by yourself, and remember we are using the sample covariance formula, so the denominator must be n minus 1. Try it by yourself. Okay, so if you have not finished the algebra, please stop the video now. I'll show you the answer. The covariance is, in the end, it's minus 270. How do we get it? You first calculate, so I calculated the averages here. The average temperature in Fahrenheit of the 3 countries is 50 degrees. And GDP per capita, average GDP per capita of the 3 countries measured in $1,000 becomes 30, right? So it's not that difficult. You can just calculate them directly from these 3 numbers for each variable, and then subtract these numbers from the observations. So W is 23, 50, 77. You have to subtract 50. Then it becomes minus 27, 0 plus 27. GDP per capita are 35, 40, and 15. You subtract 30. Then the deviations become 5, 10, minus 15. By the way, here is it's W bar, upper bar. Upper bar is not clearly seen, but I believe you understand. And then after calculating those deviations, you multiply them. Minus 27 times 5, then they become minus 135. And similarly, we multiply these numbers to get minus 405. So summation is minus 540, and then you divide it by n minus 1, 2. So in the end, the covariance equals minus 270. Okay, so it's just mechanical steps to calculate the covariance. But what I wanted to show you with from these two examples is that actually the data I changed it Celsius to Fahrenheit and dollars to $1,000. I changed their units, but basically they are still the same variables, still the same data. Changing units should not cause any difference in the relationship, right? They are basically the same data, same nature. We will study what happens if you change the measurement unit. In our example, X is temperature in Celsius. W was temperature in Fahrenheit. And we know the relationship between Celsius and temperature are given by this linear transformation, right? And also, Y was GDP per capita, original GDP per capita in dollars, but we removed 3 zeros. So that means we divide them by 1,000. That becomes Z, which is measured in $1,000. So also this is another linear relationship, linear transformation. So then what's their effect? Those linear relationships can be reflected in those covariance. The answer is the original covariance, the first covariance we calculated was minus 150,000, and the second covariance was minus 270. Seemingly they are not related, but actually they are related. Those two covariances are related, associated with, the relationship is determined by those multiplied coefficients. So in the linear transformation, in the first linear transformation, 1.8 is multiplied. So the covariance is affected by 1.8. And in the second transformation, we multiplied 1 over 1,000. That is also multiplied in the covariance. So multiplications do affect the covariance. However, the addition of 32 has no effect because we are looking for the slope, and parallel shift does not change the slope at all, right? Only the multiplication changes the slope of a straight line. So parallel shift has nothing to do with the direction, right? That's why plus 32 disappears in covariance. And same intuition holds for the variance. When we learned variance in chapter 4, we learned that additive constant, addition or subtraction, has no effect on the variance or the standard deviation. Idea is the same. Variance was about the spread. So parallel shift means nothing. Does not change the variability spread. So that's why addition has no effect. So in general, we can think about this formulation. So think about linear transformation. Suppose that we originally had x and y, two random variables, but we transform x into y, w, and y into z. Random variables, original random variables are x and y, but after linear transformations, we obtain w and z. They are a new pair of random variables. And then the original covariance and the new covariance, the covariance of the new random variables is the original covariance times those two coefficients, slopes, right? A times C. And as I said, plus B plus D do not affect the covariance at all, right? Okay, so the formula is nice. It's intuitive, like, and it's not that difficult to understand. But actually, it is a problem because as I said, no matter what measure you use, like even if it is measured in either it's measured in Celsius or Fahrenheit, basically it's the same temperature. We are using the same data. So they do not change the relationship. Changing units do not change the relationship at all. Underlying relationship must be the same, but the covariance changes, even if the underlying relationship should not change. That is a problem. So then we can explain that this way. The covariance captures the direction, whether it is positive or negative. The sign of the covariance is meaningful. However, these number 270 or 150,000, what do they mean? The answer is nothing. Those numbers change according to the measurement unit. So they mean nothing. So this is not desirable at all. We would like to make a standardized measure that only captures the direction of the unit, and that is invariant even if you change the measurement units. Okay, so we will modify the covariance to define such a variable, such a measure. That is the correlation coefficient, which I'm going to discuss in the next video. Okay, see you in the next video. Bye.